All right, get started. Welcome to Rob 311. Oh man. Rob 311, lecture 21. A lot of lectures, 21 lectures, that's pretty good. That's like almost the most I've ever done. We're going to keep going today. We're going to continue kind of on PID control. We're going to talk about loop structure, more about what goes in that control loop and how to tactically implement it in the control of a robot. And then we have maybe one or two more planned control lectures. And then I think we're going to sort of switch to like just working on control. That's kind of my plan. Something that like we haven't talked about much is feedback that you guys have on the class. Like how is it going? And how have we set up like the material and the homeworks and exam and like how is all of that working to teach you? So if you have, I think there is like a midterm evaluation thing that went around. Did anybody fill that out? You did, okay. So I have not looked at that. I should look at that first. But if you have any feedback for me, just your thoughts on how things are going, things that are good or bad or easy or hard, or this is the first time the class has ever been taught. It's a giant experiment. So your feedback is helpful. So please let me know. I'll take a look at the midterm feedback too. Homework 5 will be posted today. I'm going to try to fit in 2 more homeworks. So we have 6 total. But I'll have to look and see the exact schedule. But that's the current plan, is that we have 2 homeworks left ideally. We have about 3 weeks or so left. But that includes Thanksgiving. So I'll try to squeeze in 2, but you'll see those go up and you'll see the dates associated with that. We'll talk about it more next week or on Thursday. Last kind of announcement is, do you guys know filtering? Is filtering a thing we should cover or not cover? Who knows filtering, how to filter something?
Data?
Yeah, filter data, like for example, in your controller. So you could filter the data, it's not a thing we need to review. Who would like to review filtering? Okay. Okay, well that'll add a lecture, so that's fine. We can probably do that maybe next lecture. All right, that's good to know. Alrighty, so where are we? I'm going to review kind of the concepts that we talked about last time, the PID. This again sets us up on where we are, what we've learned. We are here. We've learned so much. So we talked about control. What's the number 1 objective of a feedback controller? What is its goal? Yeah.
Track a reference.
Track a reference. That's the game. Everything is about tracking a reference, which we might think of as making a robot do what we want it to do. We want it to track a reference. All right, so it's tracking a reference. And so that means that our general idea of a control strategy means we want this control strategy to just equal 1. If it equals 1, then our reference system, our reference trajectory will match the actual trajectory, and it's a perfect controller. Why doesn't this work? Why is this hard? Yeah.
All the systems have lag.
Yeah, the systems have their own properties. Those properties can have lag. That lag makes it not quite so easy. Good. This was kind of like setting up both why it's hard, but then also the kind of standard diagrams for a feedback controller. And we talked about each one of these is a function represented by an ODE, so a differential equation. If you've taken other feedback control classes, you might represent this as a transfer function inside each of those, but this class does not deal with transfer functions, so we won't talk about it. Do you guys have a clear picture of like what, for example, the ODE was, where it would come from for the actuator dynamics? Or is that like clear to you or not clear? Yeah.
Just be like torque equations or like
the angular or like different
angular velocity and acceleration as like the
I guess differentiable variables.
Yeah, so it would be a set of equations. So motors have 2 inputs and 2 outputs. So there can be lots of equations that relate kind of what it is that they do, but they come from Newton's second law, so the equation around inertia. We use that as KTI equals J times theta double dot plus B theta dot plus torque, alpha torque. And we also had a Kirchhoff's voltage law, which gave us the voltage relationship, which included current and its derivatives. So those two equations can be rearranged to get this relationship. We aren't going to talk about exactly how to do that because it's not, we're not really learning the tools to do that. So just know that that's what's kind of in here. That's where it comes from. It comes from the dynamics of the inertia, the dynamics of the inductance. So those are the properties that are going to govern that ODE. But we haven't really learned exactly how to create this. We're not going to. That's a little bit outside the scope of the class, but I think you should have a clear picture in your head of sort of what's going on in those, even if we haven't talked about the exact math operations. What are we showing here? What is this whole thing? What's going on there? Why am I showing that to you? In fact, that's like a good question to always ask yourself if you want to check your knowledge. You should, if you're not understanding where I'm coming from, you should also be able to answer the question, why did I show this to you? Like a lot of this content has been curated with a really specific intent. So what's going on here? Yeah.
It's the system's response to an impulse.
The system's response to an impulse. This is our impulse. These are our, what do we call these things? That's gonna be right. What do we call it? We had specific names.
Response. The impulse response.
The impulse response functions. Yes. And so what changes to make a system go from looking like this to looking like this? Yeah.
Like damping mass or spring constant?
Yeah, these physical properties change the behavior a lot. So depending on what they are, it drastically changes maybe its impulse response function, which then drastically changes what the controller is going to have to do. Do you guys have thoughts about which one of these would be easier to control? Any thoughts on that? Is that an easy, is that a thing that's we're not gonna be able to get a ton of insight just by looking at their IRFs. What if I said you want one to be able to track a faster reference? Which system would you want? Yeah, the top one. Yeah, good. So this system has kind of a lot of delay associated with it. So that's going to impact how fast the system can track a changing reference. Okay, cool, good. Yeah, so this was meant to show you that systems have dynamics. Those dynamics can be represented as an impulse response function. If you know the impulse response function, you can get a kind of a feeling for the lag or delay that's added by kind of looking at the shape of that curve. We also mentioned that if you take an input, this guy, and you have a system description, maybe it's impulse response function. Do you know, we said, I don't know if we actually talked about this, but you know you can get the output from the input and the IRF using convolution. So this is the function definition that describes the output. Who knows convolution or has heard of it? You guys know that if you take the input of a linear system and its impulse response function and you convolve them, it will give you the output of that system. That's another reason why we touched on this, is to kind of just help you get familiar with seeing these concepts. Okay, so this is kind of refreshing these concepts of system dynamics. Dynamics exist in each one of these blocks. Those dynamics add delay, they add challenge to the physical system, and this is kind of where we would get each one of these ODEs. What do we say about sensor dynamics? Fast. Which means there's going to be minimal lag associated with your sensor. So that's another way of saying the actual output, the measured output should be very, very close. Even at high frequencies. It's going to track really closely even when it's oscillating very quickly. Yes, that's good. That helps the whole system. And that's kind of a desired property of sensors. You want them to be fast. Does a encoder have like an optical encoder? Does it have dynamics? I would say it doesn't, because it is a direct, like you're looking at the actual physical change and it's being measured. So there's no delay in that physical change between when it happens and when it's read. For example, if we have this IMU that had this big mass on a spring, that mass is the size of that mass is gonna govern how that sensor senses. In an encoder, there's no concept of that. It's motion, that motion is read. There's no dynamics. Make sense? Okay, good. Trying to think of any other challenge questions I can ask. Now's a great time to like ask questions on this content. You guys are good with it? Awesome. Okay. So now we're kind of going back into PID. The number one game is drive the error to zero. If the error is driven to zero, the system is acting like unity, has unity gain. That's what we want. Our control law is going to operate on the error, which is going to be the difference between our reference and our measured output. And everything's going to sort of, for now, everything's going to be about that error, about driving that error to zero. We defined three terms, P, I, and D, and the total controller effort is the sum of those three terms. And we talked about how these terms are created. You guys are comfortable with this, I think. What's going on there? Why is there a tau in there? There's no tau in anything else. What's going on there? Yeah.
Can't really, your bounds can't be the same variable as like the actual.
That's true. But why is this bound a different time variable? It's integrating over time to get a single value, and that area that it's integrating over time is time, but it's not the same time as t, which actually is one of the bounds. So does that make sense? It's integrating over. If you want to evaluate at t equals now, we have to integrate over time. So we're not integrating over t time, because that's what we're interested in. We're calculating the value for t equals now. So we're going to integrate over time in the past. That integral from t0 to t goes up to time equals now of time tau. Not sort of a different t, but it's still time. Make sense? So I'm trying to think of like challenge questions to make sure to kind of check and see how well you guys are tracking this. Let me think. I think I'm good with this. I'm gonna keep going. We did this example, which was cool. Almost all of you got this. This is great. If you didn't get this, if you can calculate this and these terms, then you're tracking PID well. If you can't, then that would be bad. So if I had more time, I would have created a couple of versions of this, a couple of exercises, just as practice. But first, identify your error function, then you're going to manipulate that error function. It's easy to kind of figure out its derivative and integrals once you define the error function first. Then we just sum them, multiply by their PID gains. This gave us like some vocabulary about how to talk about control, talked about these concepts in the time domain, settling time, rise time, percent overshoot, steady state error. Just give us a vocabulary for me to talk about. And then we talked about like this being a type of test called a step response test. And that's it's pretty much the most common way to tune a controller is to use a step response test. In order to do this type of test, you have to be able to see your data. So you have to be able to save your data and look at it. We've learned how to create this data matrix and save it. So you guys could do your own step responses. That would be very doable. We're also going to learn tomorrow a way to plot your data live. We also talked about kind of like how to tune. We have to set these PID controller coefficients. We talked about how to do that. There's like some infrastructure on it called Ziegler-Nichols. We did kind of a shorthand version of that where we increase KP, back it off, and then we're going to increase KI, remove steady state error, and then increase KP and remove oscillations. We talked just for a second about reference trajectories. The only thing I really wanted you to know is that the higher the frequency content and the reference trajectory, the harder it's going to be to track. The harder it is to track, another way to say that is the controller gain will not be 1, right? Does that make sense? If I'm saying the controller gain is 1, that's equivalent to perfect tracking. So if it's harder to track, I mean this controller gain will stop being 1. Will it be greater than 1 or less than 1? So let's say I'm trying to give it this reference to track. So a fast trajectory. I wanted to track something moving very fast. We talked a little bit about what do we think it's going to do. And you guys knew this. Yeah, what's it going to do? Yeah, so
it's gonna have like the amp.
It's gonna kind of lag behind a little bit with a small amplitude.
yeah, it's going to start lagging behind. The amplitude's going to decrease, which is going to make the overall gain less than 1. Yes. So the gain for this would be 1 for low frequencies. And then as the frequency increased, we'd start to see the gain start to become less than 1. And eventually the gain would be 0. Cool. Okay. We did this tuning example, which was pretty neat. You guys did great on that, turned it in. Here's just an example of what I did. This shows all, if you right click and have it show all the characteristics, that's what's being shown there in MATLAB. So you have practice kind of tuning it in MATLAB, practice looking at your step responses and analyzing them and viewing their different characteristics. Yeah? You guys feel good about all this? Awesome. Okay. Now we're going to go into actual lecture content. Okay, so now what we're going to talk about is how do we actually implement this in code. This is maybe review for some of you, but I want to make sure everyone kind of knows it. We're going to go through like your control loop structure. These are concepts you've begun to kind of see in lab, but now we're going to kind of talk about it formally in class. Your control loop's going to iterate every, like in our case, 1/200 seconds. And there's some few things that we want to talk about or discuss when we think about implementing control in software. A couple is how do we calculate the derivatives? And how do we deal with nonlinearities? And what are they? Let's talk about control loop structure. This is what we talked about in lab in the past. What's the first thing that your control loop does? Yeah. It collects data from sensors. Yes. Then what does it do? Do you know? Or like what's the next thing it has to do?
Calculate the error.
Yeah, calculate. I'm going to say call that as a whole. Calculate actuation commands. Then it has to actually send those commands, it has to execute those commands on the actuators. And we need to save data and update variables. Those are kind of 4 jobs that are going on inside your controller. So refresh data, and I gotta write this again, I guess. Use feedback to determine controller commands. Send commands to the motor. And transition variables. That's it. So that's all it's doing. It's gonna do that real fast. Data collection. Okay. First thing we gotta do is collect data from all of our sensors. Generally, the way this would look normally, so it would be a series of communication library calls. What's a communication library? When I say it would be a series of communication library calls, what does that mean? Yeah.
We have like our like messages.py file, which has all of the different message types that we have available to us. So like
You have to essentially pull some data from, I guess, the Pico through that.
Yeah, that's how we do it in our system. So our system, the data are being refreshed automatically kind of in the back end for you. So you don't have to do anything to get the data. The data just appear in these state variables for you, which is awesome. It's a very, very clean and efficient way to do it. If we didn't do that, you guys would have to get those data on your own. You'd have to write some commands that say, get your motor encoder value, or get your IMU value. And there would be commands that you can look up and send that would get those data. You don't have to do that here, but I want you to know that that's typically how it would work. But typically you'd have to get those data from a function library call, which would say like, IMU, give me your data, and then the IMU would send its data back. So you'd have an API, like a Python function. I showed you the one for the IMU actually. It was a really long Python file, it had a bunch of big blocks of numbers. That was its driver. We would use that driver to get the data. Typically, one library call like per sensor. So you would be getting it from all your different sensors. What's another, I'm calling it a communication library here. What's another word? There's a few other words we've used to talk about like this concept. Anybody know any? When I'm saying a series of communication library calls, there's at least, like I can think of two other ways that would be said in this class. What else do we call these things? Yeah.
Hey, I don't know if this might,
I was thinking of like you're like subscribing to like information.
I don't think that's
That's not what I'm looking for. What I'm talking about is an API. A driver is also call it an API. Peripheral interface. Somebody has created a like language for you to ask for data. We also call it a driver. These are the software driver is this concept, or a communication library. They're all kind of the same. This is information I think this is review. Do you guys feel like this is review? You guys track this? You know what I'm saying? Okay. All right, good. So normally you'd have to do a series of like library calls, asking each sensor for its data. You don't have to do that. So in our system, the data are refreshed automatically. How? The Pico collects and sends to the RPI. So we've streamlined the process for you. But you guys could do it on your own. That's kind of what I'm trying to convey. We've done it for you, but you guys could do this. This is an example where this is just us kind of getting the data like you've seen before. Okay, step one, get the data. Okay, step two, this is kind of where the meat of today's lecture is actually like building these actuation commands. We're talking about PID. We're gonna go through these different terms and talk about like what are some nuances to calculating these terms. So this is your proportional law. UP of K, that means that's the controller effort from the P term at loop index K. So that's just gonna be KP times the difference, YK minus RK, or KP times error, easy. Most of your controller effort will probably come from this term. So the proportional term adds a ton generally, usually adds a lot to your controller. That's where a lot of your controller effort's gonna come from, and it's easy to implement, that's great. Integral term. So this is how I would potentially implement it. I'm implementing it basically in 2 lines here. These lines, this is like half math, half code. So like that's kind of trying to make sense. I thought it made sense, but this is the integral. So you're just gonna create a variable that's a running sum. You're tracking the error, you're just always adding to it. That's integrating your error. So you have one variable that's just the sum. So you have error sum is gonna be your current value of error plus error sum. That's gonna track that. It's gonna integrate your error. So that's not too hard. So now if we want to talk about the controller effort, we just do Ki times E sum times dt. And that's a Riemann sum approximated integral. Do you need the dt?
If you don't put it in there, then you just account for it and keep in the constant.
Right. So like, I'm gonna say the dt can be omitted because that's just gonna change the value of Ki, but the value of Ki is arbitrary. So you don't even really need to include the dt. It would just scale your Ki term. Does that make sense? So so this, boom, you can calculate a running integral for your PID controller. The integral term is susceptible to something that can be problematic. Do you know what it is?
The saturation of especially when it's building up, that's a giant error at the beginning.
Yep, so it's susceptible to saturation. Now we're gonna talk about what saturation is. Saturation is a type of nonlinearity. So if you're using the kind of fundamentals of linear systems, which we're using in this class, that will break down from saturation. Okay, so let's talk about this. So as a reminder, your integral effort is going to track the integral of this error. So it's going to be summing the blue, removing the red, summing the blue. Make sense? That's the kind of effort of the integral term will be proportional to that area. This allows the controller to add as much effort as needed. Agreed? This area can be extremely large. If we're taking a big step, and it takes us time to get there, this area can be very, very, very large. Can your controller or actuator provide kind of infinitely large effort? No. So that's kind of where the issue is. So I'm gonna say steps could be arbitrarily large. In your application. What I kind of mean by that is, you might tune your controller with a step response. That would be a very common kind of way to do it. But in your application, your reference is going to come from some other, your objective and then the dynamics of your system. So the error step that it sees could be very large, very different than your step response. So there's if you tune it for one step, and it sees a really large step that could contribute to adding a lot more error than maybe you were expecting. So in applications, error can really accumulate. Can your controller always provide this effort? No. That's what we discovered. Think about like, this is, one easy way to think about this is like your gas pedal in your car. If you, let's say you give yourself a step velocity, you want to go from 60 to 120 on the freeway. So you're going to floor your gas pedal. And it doesn't really, at that point, it doesn't matter how much extra controller effort you give it, there's nothing it can do. It's going as hard as it can. That's a nonlinearity, that's saturation. Where does saturation come from in robotics? Typically it comes from pulse width modulation. Pulse width modulation is something I've been trying to like work into this class for like 2 months. So now I finally have a good time to talk about it. You guys already probably know pulse width modulation, but I want to just make sure we talk about it. Pulse width modulation is how the voltage command is provided to your motor. That's how it actually receives electrical power. It receives it from a PWM signal. The PWM signal is a quickly oscillating voltage that varies between 0 volts and supply voltage. The average like electrical voltage applied is applied by varying the duty cycle. By varying the duty cycle, the applied voltage can be varied. So this is our PWM signal. It has two like salient characteristics. One is the duty cycle. That's how much on is it compared to how much off. And the second is its base period, or its frequency. How fast is it oscillating? Let's say I have a PWM with 50% duty cycle. And I have one that's oscillating at 200 hertz and one that's oscillating at 1,000 hertz. Do they have the same average value? Two PWMs, each with the same duty cycle but different frequencies. Is their average value the same? Yeah, it's the same. So like the base period or the PWM frequency is a number that has a function, has an importance. It needs to be higher than some threshold, but then it doesn't really matter how fast it is. If it's higher than that, it doesn't really matter. What do you think, where do you think this constraint on PWM frequency comes from? Any idea? This is a really hard question, actually. How about this? If the PWM signal, if we're applying a voltage to your motor and a pattern that looks like this, what will the pattern of the current look like? If it's sufficiently slow, you agree that the current will follow a similar profile. We apply voltage, that voltage will create a current. It's going to follow a similar square wave. But if we increase the frequency of this PWM a lot, eventually the current would sort of get filtered by the dynamics of the motor, the inductance, its inertia. So rather than seeing you see a voltage that looks like this, we might see a current that looks smooth and flat. That's really what you want. So as long as your PWM signal is oscillating faster than what it gets smoothed out, it's fine, and they all usually oscillate very, very fast. So to send electrical energy to a motor, we vary this duty cycle. That's varying the motor seeing battery voltage, 0 volts, battery voltage, 0 volts. The dynamics of the motor and physical system, smooth. The rapidly oscillating voltage. What's the max PWM value? 100%. So that's gas pedal fully down. So this creates a nonlinearity when the controller, let's say, maxes out. Okay, so now we know like saturation is a thing. Now we know where saturation comes from. It comes from our gas pedal being all the way down. What effect does it have? Is that a question?
Yeah, I was just wondering, like how fast are PW, like what's a typical like PWM frequency?
10 kilohertz would be a common one.
Fast, okay.
Yeah, really fast. They can be in the megahertz range. Okay, so this is why this matters. The maximum effort nature of actuators is known as saturation. That we sort of covered, I guess. Yes.
When it's at 100%, is it still like
Oscillating between on and off, or is it just like always on?
It's always on. 100%, it's always on. What can saturation do? Any idea what saturation can cause? Some of it's on there, but some of it's not. What saturation, any idea, like what does it do for your car? Any idea? It's going to cause inefficiency. And excessive overshooting. It causes excessive overshooting because it's going to build up all this error that it then has to remove. The only way it's going to remove that is going way over the reference. So to address this, sometimes a saturation limit is used on U I of t. What is U I of t? What is this variable? When I say use to limit U I of t, what does that mean? Just to make sure we're on the same page.
The output of in the PID loop of the integral term.
The controller effort specifically coming from the integral term. Yeah, that's right. So we would create a saturation limit. So we're not going to let the integral term build up greater than some number. This can be implemented with basically an if-then statement. It's not, so this is easy to implement. One thing that you could do is check to see if your controller effort is ever from the integral term is ever greater than, let's say, 50% of your duty cycle. Then don't limit it. Don't let it go more than that. That'll prevent it from having this issue. So make it something like X%. I'm going to say 50% could be a good starting point. Do you know what I mean when I say limit the PWM duty cycle to 50% for the integral term? Is that clear to you, like what I'm saying there? Somebody who's not talking much, can you help me, just help me understand, like, do you know what I'm saying? Who knows, do you track like how you would do this? You're creating your controller effort terms, your 3 controller effort terms, P, I, and D. Then you're gonna watch UI and say like, if UI is ever going to duty cycle greater than 50%, stop it. Set it equal to duty cycle at 50%, and don't let the error grow. And that's all you do. So these are some things that are this is an example of like if saturating. So this is a cartoon, this is time. This is like what the PID controller thinks it's sending during saturation. This is what it's actually sending. Does that make sense? So we're truncating the controller effort being provided because it went above the PWM 100% duty cycle. And then this is what it might do on the, so this is our reference and our output. What we'll see here is like basically it's saturated, it can't reach the reference, and then what we see is this kind of a lag that's induced. This is kind of called wind up.
Lost it.
This is wind up induced lag. Yeah.
Why would this saturation limit need to be implemented for the integral term, but not the proportion or derivative?
Because those terms won't likely build like an integral will. An integral will build way faster.
Right.
Yeah, so you just don't see it. It won't even for let's say for a fixed reference and output, integral will grow unbounded, but your proportional term won't. That's what I think of it. Yeah.
Oh, like something that I've kind of done in the past, like counteractive saturation would be like more of an I zone, where if it's in this zone, it doesn't actually increment the integral, and in
Yeah.
fact, it resets it to 0. Is that another way?
Yeah, that's another way to do it. So like for this, it might be, don't let it, that would not be maybe saturation, that would be maybe something else.
But it kind of like prevents the I guess like the I term can still, if it's not responding, then the I term can start saturating if it's like continuously off, but
Yeah.
I've never lost to hit the point where saturation could be a thing, because if it's actually responding correctly, it would then go back to 0. It would keep resetting the integral to
Yeah.
0.
I think that makes sense, and I also think you guys should feel empowered to take these concepts and mix them up and try things that occur to you that seem like they might help. So like that is something that you can and should do for this project, and it could be things that look like this. You observe something with the ballbot, oh, I think it would, I'm looking at my controller efforts and I'm seeing that this one of my controller efforts is always getting too big and I need to figure out a way around that. You can just do that and execute it, and it can be things like what you're saying, and a lot of times those actually like are really helpful.
Do you find like the maximum effort for this, like
When you're saying like 50% of the maximum effort, what exactly is the maximum effort?
100% duty cycle would be maximum effort. So in this case, you guys we abstract the duty cycle from you. So you give it a torque, we convert that torque into a duty cycle and send it. What you're really doing is setting a duty cycle. At some point, that torque will saturate and your duty cycle will be at 100% and nothing else can be added.
so this like when you're talking about like putting a limit on it,
This isn't specifically just like the derivative component, it's like the whole duty cycle that's
created from when you
put them all three together.
No, just the integral component.
So then would you have to specifically convert only the integral component into a duty cycle first to like
Yeah.
put a limit?
Yeah, so they would all be duty cycles. Like it's only this particular project that you're able to do it in torques because
But
we
when
do.
you, like, as opposed to, I guess I was thinking like
adding all of the values of each individual term together first and then converting them into one duty cycle rather than putting each component into a duty cycle.
You usually want to track the individual contributions of all three. You will eventually sum them, and that's going to be your controller effort. But how the efforts are trading kind of during the control process tells you a lot about what's going on. So you would want to save them and look at them or have access to them, even though you eventually are just going to sum them and send them.
so but you'd be looking at them in
Like as a duty cycle rather than as their like actual value that you calculated.
It could be, yeah, ideally you'd look at it in a duty cycle.
And then
Because
you
then
put the
you
limit.
know when it's going over 50, but yeah, that sounds right. So like also if let's say you're doing this anti-wind-up concept, you would want to set it equal to not let it go over 50%, and then what you'd want to do is like not let it integrate. You want to stop the summing, so that otherwise it's just continuing to sum and build this error. So you would say, okay, the integral term has reached its maximum. I'm now no longer going to let it integrate anymore until it starts to remove some of that. Okay, integral terms add a delay or lag, which we see in this windup, known as windup. Okay, so that's saturation, actual saturation. It's a real thing. It's a nonlinearity. It's a thing we all have to deal with. There we go. Okay. Next, just like derivative commands. So we've talked about proportional. It was easy. There's nothing to say. Integral, you have to watch out for saturation. So we talked about that, how to create the running integral. Talked about saturation. Now we're going to talk about the derivative commands. So, small nuance with that. calculating a numerical derivative or the derivative term requires a numerical derivative. You have to calculate a derivative in your loop. Most common is the 2-point finite difference. Okay, so what this is saying is our variable dE by dk of value k is going to be ek minus e to the k or e of k minus 1 times dt. So this means you have to track your previous value of error. You need access to that in the loop. This guy, e of k, that's your error of the current loop value. E of k minus 1 is your last loop value. So that means you need the error from the last loop. That means you have to say that. So variables saved at the end of each loop. Then we just calculate our controller effort by multiplying the d gain by our derivative of our error. What do you think you have to watch out for this one? Noisy signals. Because you're doing a 2-point difference derivative, it can be very, very noisy. So your derivatives can look really crazy. Clean signals are needed to gain useful derivative information. Yeah.
I was just curious why you're multiplying by dt
No,
instead of
It
dividing.
should be divided. Thanks. I was just testing to see how long it would take you guys to catch that. Are our signals noisy? Yeah.
Is it kind of like the integral term where the dt is technically not needed since it's supposed to be a constant here?
Correct. Because it would end up just scaling this guy. Yeah. So our signals, are they noisy? Like, do you think we can use derivatives? Is anybody using a derivative already? How's that going for you? What are you seeing? A lot of noise. And are you taking the derivatives of this guy? So I would say the IMU is actually pretty clean, surprisingly. It's not perfect, but it's a pretty clean signal that IMU provides. So that's good. That's going to be helpful for your derivatives. How about the encoder signals? They're interesting. Are they clean? This is weird because they sort of are clean. If you look at them, they're very clean signals, especially when you look at them from far away. But they're digital signals, they're quantized. So if you try to take their derivative, it can look really crazy. So these are clean. I'll say clean when viewed at larger timescales. But quantized. Why are they quantized? What's quantized? What do I mean by quantized?
It's like step.
Yeah, they're kind of like stair-steppy. They're quantized because in order for an encoder to understand that angular changes occurred, it has to see a pulse. You can't see fractions of pulses. So there's gonna be some quantization that occurs. So they are clean, actually. They're clean, but they have quantization. When you try to take the derivative of something that's quantized, it's gonna look real crazy. So, like, what could you do to address that?
Take it over a larger DT.
You could take it over a larger DT, yes. That's like one thing you could do, would be track, instead of a 2-point, it would be like track kind of many points and do an average across some larger length of time. That would work. But it would still give you some quantization because it would be like fundamentally discontinuous, but that would help. Yeah,
I was gonna take a moving average of the encoder data.
moving average would also work. Yeah.
If you like just smooth it and then like take derivative.
Did you say smooth it?
Yeah.
Yeah, so like, but all of these are essentially the same thing, which is you can filter it. So we can filter that signal and then take its derivative, and that would give us a clean, a smooth derivative. But filtering was a thing that you guys wanted to discuss, which we will at probably like next lecture. Cool. So for the derivative, we use these finite difference derivatives. You're going to be tracking variables, from your previous loop. That's really normal. Calculate your finite difference derivative and keep going. There are lots of intelligent ways to take derivatives that are better than this. This is just the most straightforward and works most of the time. Like you can probably get this to work. It's not intelligent, obviously. It's really, really simple and noise prone, but it still is effective. There are other more complicated versions where I'm gonna not teach you those. I think this is all you need. Okay. So we've kind of gone through, this is like how I'm representing a control loop. Control loop has these functions, we're updating at 200 hertz. We've kind of gone through these two first blocks. These are basically one slide each. But I do want to re-go through the control stuff the control lecture we saw in lab, because you guys haven't seen that in actual lecture content. So I just want to talk through the control loops. And this is like a great time to ask questions or make sure there's no blanks on these. I left them blank free, so we can just talk through them. You guys know, so now we're talking about control loop. We're building the controller effort variables. Now we're talking about like, what are those? What are your controller effort parameters in your control loop? We have two controllers that we're talking about. They're running in parallel. And then each one of these controllers controls in two planes. We have the two fundamental planes that we're dealing with. And then we sum their efforts, convert it to the torques for the three motors, send those out. Does this make sense? You guys track this schematic like, well, okay, good. Okay, so we began lab by just doing a simple P controller, and at that point we hadn't talked about PID. We got to this by sort of saying it makes sense that if it leans, we want it to restabilize. If it leans further, it's going to be harder. So we kind of derived from common sense this idea of a proportional control law. Yeah.
I had a question on the previous slide.
Yeah.
For when it says like the desired movement input, like they're kind of separate.
Yeah.
Is it also possible that like you could combine them by making the desired movement input just change the desired lean angle
Yeah.
instead?
Yeah. So exactly how this is done, there's tons of options. We have done the lean angle option. So that was the first controller idea that we thought of. It was basically have the controller input just change the lean angles. And so you lean it forwards, wherever direction it's leaning, it's going to be rolling in that direction. So we did that. It was very difficult.
Yeah.
And one thing is like once it starts leaning,
It doesn't stop.
yeah, that's an acceleration. So like it's just going to keep accelerating if you keep it leaning. So it just would go faster and faster and faster. So we're kind of working on that. We have some new ideas that we're working on now that might work their way back into the course at the end. But yeah, so we've done that. You could do exactly what you're saying. I kind of like this idea so far, which is we have a balance controller running all the time. The steering controller is going to allow you to rotate it around the z-axis and drive it along the x-axis. So it only drives along the x-axis and only rotates about the z-axis. That's one idea. As opposed to another idea would be to have it be able to drive, do no spinning, and have it just be able to drive in any direction. That's what we first did. Okay, cool. This is pretty similar to any robot that you would build. What makes this maybe a little harder is that there's this conversion concept from planes to the real motors. Like that's pretty like detailed and only a part of this project. And then also the concept of like these two controller types, like a balance and a steering. That's also like a detail of this project. So there's similar concepts in other and projects robots you might build, but it probably wouldn't be exactly like that. You guys tracked this? This was I've kind of rewritten this as in terms of K, like loop index K. This was our control loop for the balance controller for one plane. So we just got the control law by saying it's the error times KP, and the error was, since it was referencing 0, the error was essentially the variable. And then we did two planes. Do you guys understand this as much as you can, like 100%? You feel super comfortable with what's going on here, how this like kind of diagram goes back to the control loop diagram that we were showing. We were just showing the controller ODE blocks. Like this is the same thing. Does that make sense? Okay, good. Awesome. And then this is kind of where we ended. This is where we are now, which is now we have a balance controller. We have a vertical axis controller. Each one of these creates a torque, z, y, and x that gets summed and translated. And what we're going to do is kind of figure out the best way to use this controller to do not just steer, not just kind of rotate and balance, but then actually steer. One of the reasons why your homework assignment was the rotation part was to give you this understanding of this mapping between torque and like rotational velocity, so that when you started to use your controller, you kind of had an idea for, if I assign this button to this torque, that's going to make it rotate at this speed. Does that make sense? That was the intent behind that. Okay. There was one more thing I wanted to mention. Any thoughts on this? I'll try to think of my one other thing, yeah.
What is the scene of the diagram?
These guys?
Yeah.
So this is an equation. So this is saying theta desired minus theta x equals error. So when they're minus, it's just algebraically subtracting that variable. Each signal, like each arrow, is a data structure. And each block is typically a math operation. Cool. Okay. I'm just going to do these last two slides and I can maybe end a little bit early, unless you guys want to talk about other concepts. I just threw these slides a little faster than I was expecting. Okay. So now we've done how to collect data. Certainly in your setup, it's collected for you. How to create control laws and actuation commands. Now we're talking about like how to send those actuation commands. This is extremely straightforward in our project because of the infrastructure again that we provided. So you're just going to set it up like this. That's how we send the commands to the motors. You guys could also, like if we hadn't done this is also something you guys could do. You could find examples of sending PWM commands or however it worked with whatever you were doing, you can usually find like tutorials on YouTube or on Adafruit or SparkFun. So what I kind of don't want is the fact that we've done this infrastructure building for the PCB and the Pico to now hold you guys back after the class. That's what I'm trying to prevent, is that I'm also, at the same time, I'm trying to get you guys access to these boards later. So like if you guys want to keep building robots, now that you know how to use all these infrastructure, you'll be able to. Those are 2 side notes. But okay, at the very end of your loop, you're just going to set your motor commands. It's going to apply this voltage to the motor. So in our world, we're going to take that torque, convert that into a duty cycle, and send that based on the properties of the motor. And this is basically always, sending the commands is almost always just a couple of lines of code. It's not like a lot of work to send these commands. So it's a couple of lines of code here, but even if you hadn't, we hadn't abstracted it, it would still be something very straightforward. And then the last thing is this loop, changing the variables at the end. So the variable at the very end, you have to create your data matrix. We've talked about this. This makes it so you can save data and look at it. But you also have to transition your variables now. So sometimes now you have a loop that's operating not only on the current values, but the values from your last loop iteration. For the very end of the loop, you need to set all of your current values equal to your previous values. Then the next time through, it has access to those previous values. So that's what's going on here. Like transition variables, error x prev equals error x, error y prev equals error y. Now the next time that enters that loop, you have access to your previous error. So, nothing too shocking. Does that make sense? Okay, we have like sort of 15 minutes. This is all the slides I have. This is actually I was hoping to get through. We can talk about filtering. We could just break. I could talk about concepts from this lecture. This was a little faster because some of that you've seen already. What do you guys think? Who wants to just break early? Who wants to talk about something specific? Why don't we break early? I'll be at office hours, and then whoever wants to stick around and chat, we can. Does that sound good?